Well, good afternoon, or good morning. It's 11:32. I've just sent the invite. Hopefully you have seen it and will soon be logging in. This is Math 237, Linear Algebra. We are in section 3.1, which is, chapter 3 is determinants, 3.1 is determinant of a matrix. And we're on example 4 on page 113. So that's where we'll be beginning. I'm kind of just killing time talking, hoping someone will show up, but so far no one has. So I'm going to move this out of the way so it won't be in our way of writing. So here we had talked about how you determine a determinant, okay, by expansion of cofactors. That was the theorem 3.1 at the top of page 113 we had just talked about. Let's actually do example 4 now, okay? The determinant of a matrix of order 4. These are a bit bigger, okay? So let me get my pen set up here, okay? And here is matrix A. 1, negative 2, 3, 0. Negative 1, 1, 0, 2. Zero, 2, 0, 3. And 3, 4, 0, negative 2. There's your matrix. Okay, I hope I copied it right. Looks good to me. Okay, now, how do you determine the determinant of it? Well, when you're going to do a determinant, always look for the row or column with the most zeros in it, okay? And that, I hope it's pretty obvious to you, third column wins the show here. So the determinant of A, that's the shorthand way of writing it, is equal to, now, this number 3, okay? First determine the sign of that position, plus, minus, plus. So that's a plus position, the 3 is a plus, and that would then be times the determinant of everything that's left when you wipe out the first row and the third column. Okay? So that gives you the determinant of negative 1, 1, 2, 0, 2, 3, 3, 4, negative 2. Okay. Now, that's a 3 by 3. I'm trying to remember. I still don't think they've shown you the quick way to do a 3 by 3, and now I can't remember. Oh no, that's coming up later. Okay. So let's do it their way to begin with. All right. Here you have two choices. You could go with the first column, because that has a 0 in it, or the second row. It has a 0 in it. It really doesn't matter, okay? It really doesn't matter. Let's just go with the first column, okay? Now, don't forget your 3. That's there from before. And then that's multiplied by, you're going to wipe out we're going to have a couple of things. We're first going to do first row, first column, and that position is a positive position, but it's a negative 1 in there, and that's going to be times the determinant of what's left, 2, 3, 4, negative 2. Okay, that's the first part of it. Now I'm going to erase my construction lines here, or at least one of them. And then the second entry here is that 3 down there. Well, that's also a plus position, plus minus plus. So that's going to be plus 3. Now wipe out first row for third row, first column. And you're going to have the determinant of 1, 2, 2, 3. All right. So let's do step at a time here. 3 times -1 times, let's do the determinant here, -4 minus 12, that's going to be -16, plus 3 times 3 minus 4 is a -1. Okay, so this will be 3 times 16 minus 3, which would be 3 times 13, 39. Okay, let's see how they did. Oh, they got it too. Perfect. Okay, now notice when they do theirs, they put all that stuff about the cofactor, you know, the adding the two suffix, what do you call them, subscripts, and doing -1 to that. That's just, that's just a lot of extra work, introducing a lot of places you can make little stupid errors. If you just count the rows column, plus, minus, plus, minus, plus, that takes care of it. That's the only reason they do that other part, and we got the same answer in way fewer steps, and I think with fewer possibilities for error. Okay, now now they're going to get around to showing us the alternate way of doing a 3x3 matrix. So let's use the one that was just up here. Okay, so I'm going to erase what they did. I'll leave the answer, but erase what we just did here. Okay. All right. Now, determinant of A would be 3 times. Now, here's how I like to do a 3x3. I'm also going to erase my construction lines here so they won't be as confusing. Okay? Now, what I'm going to write is not really a determinant, but we're going to treat it like a determinant. What we're going to do is take this determinant, -1, 1, 2, and rewrite the first two columns, -1, 1. Take the second row, 0, 2, 3, rewrite the first two columns, 0, 2. Take the third row, 3, 4, -2, 3, 4. Now that's not a determinant because it's not square, but this is the simple way, in my mind, to do a 3x3. Okay? Down diagonals, just like in a regular thing, are always positive. Okay? Now we got our 3 here. Don't forget about our 3. Okay? Everything else is going to be algebra. So multiply those 3 entries together. Two minuses make a plus, and 2 times 2 is 4. Okay? That will be a plus 9. That'll be a 0 because you got a 0 in there. Up diagonals are always negative. Okay? So now I'm going to, for right now, erase those construction lines just so you'll see better. After a while you'll get used to them and you won't pay that much attention to them anymore. But the up diagonals are always negative. Well, this is going to be -4 times 3 is -12. This up diagonal is going to be a positive 12 because it's a minus 12, so that's a positive 12. Right now I can see those are going to 0, and your last one is just 0. Look at that. Okay, so what do you have? 3 times 13 equal 39, and I erased the answer, but that's what it was. So much easier than expanding the cofactors, okay? But it only works for a 3 by 3. So if you got a bigger one and can get it down to a 3 by 3, then stop there and do the easy way. Most of the time it's easier anyway. All right. They do an example 5. And example 5 is also found at larsonlinearalgebra.com for an interactive version of this type of an example. So let's do example 5. Okay, let me erase all this. And here's example 5 on page 114. Here's your matrix. A is equal to 0, 2, 1, 3, minus 1, 2, 4, minus 4, 1. Now, to keep from writing it over with, let's just say the determinant of A is going to be kind of like the determinant of this thing, though it's not going to actually be a determinant, but we're calculating a determinant, and all we do is repeat the first 2 columns. You can do it 2 numbers at a time going across, or you can just repeat the first 2 columns. I'll do it the second way this time, just show you. 0, 3, 4, 2, negative 1, negative 4. Now, let me make sure. Yep, got it. Okay, and what's the determinant of that? You do your down diagonals. Hey, that first one's a piece of cake. 0. Anytime there's a 0 as a factor, it's going to be 0. Number 2, 4 times 4 is 16. Third, minus 12. Okay, then let's do the up diagonals. And again, just to help you see it better, I'll erase my construction lines there. And maybe you'll see better. Minus this up diagonal. Well, that up diagonal was a negative 4, and minus that is going to be a plus 4. This up diagonal is going to be a good old 0 again. And this up diagonal is going to be a minus 6. Okay, we add those together. 16 plus 4 is 20, minus 18 equal 2. Yep, that's what they got. Much easier way to go. If you have, I think both of you are already in your physics courses, and you're also in your calculus course where you've been doing cross products. I don't know if you've done them in physics yet, but you will. But you've already done them in Algebra 3, and a cross product is so easy to do with this technique. And that's where if you were wondering where you've seen this before, that's where it was. Okay, there's a linear algebra applied at the bottom of page 114. It says, recall that a tetrahedron is a polynomial consisting... Oh, Dawson's here. Welcome, Dawson. You're on your iPhone, I see. I don't know, I don't think I've blocked you to keep you from talking. I don't know if you can communicate or not. Can you? Let's see, today is 16th, 17th. Yes, I can hear you. Good. You hear me all right, too?
Yeah.
All right. How does this seem?
Good. I can't see, I don't see your computer screen.
Oh, you don't?
No, I just see the top of your head.
Okay, I wish you didn't see the top of my head. I might have to call my IT person in here. It's my wife. Karen? He can't see my computer screen. He can see the top of my head. And I was seeing the top of my head before he came on. So where would I go?
Just open that up.
Which?
The button.
This
green one. Yeah.
Okay.
All right. So you can see his, but Are you sharing?
You see my wife now too,
yeah,
right?
Hey,
Okay, share screen. Maybe I forgot to do that.
Yeah, where are you writing?
Okay, on
Whiteboard.
Yeah, here. Well, yeah, I think that was it. Oh no, there it is.
There.
I'm right there.
Okay.
All right, Dawson, can you see the whiteboard now?
Yes.
Say again?
He said
Yeah, I can
yes.
see it now.
You can. Okay, great.
So you have to always share.
Yeah, I forgot to hit that button. So anyway, you missed the first part of the lecture, and it'll be on Screencast-O-Matic. I am recording there too. So, do you happen to know if Zoom records? Karen said she thought it did, but we don't know how to get it to connect with Blackboard.
I'm not sure.
Okay.
Never used it before.
Okay. Well, I don't know if you figured out where we are now. We're right on page, we're in chapter 3, determinants, 3.1, determinant of a matrix. Where we left off last time was on page 113, and I did example 4 and example 5, and we talked about doing the 3x3 matrices using the, expanding them and going, which we did in pre-calculus and then Cal 3, and you probably have done in physics 2 when you did cross products. So that's what we just finished doing. And at the bottom of page 114 is a little blurb on linear algebra applied, saying that, recalling that a tetrahedron is a polyhedron consisting of 4 triangular faces. Okay? Now, the one they show over here, I don't know if you can see the face. You see 2 and the base. That's 3 of the 4. The back side that you can't see is the 4th face. But anyway, one practical application of the determinant is finding the volume of a tetrahedron in a coordinate plane, which is sort of interesting because it's a 3-dimensional plane and you can still find it. With those, the 3 ordered pairs there, 4 ordered pairs are your coordinates of that tetrahedron, the 4 points on the tetrahedron, but you always put a 1 as the last digit of that. And then you do plus or minus 1/6 of the determinant. Pardon me? Are you there?
Yeah, I was talking with somebody else.
Oh, I see. Okay. I think there is a way that you can block your voice if something like that does happen, but then be sure to turn it back on. Yeah, because I had a phone ring earlier, but I didn't want to block mine because I was afraid students would think I'd left. So sorry. But anyway, that's at the bottom of the page. We're going to do this somewhere later in this chapter anyway. So they did it here, but we'll do it again later. So don't sweat that. Now, moving on to page 115, triangular matrices. And you remember what these are, right? The upper and lower triangular matrices?
Yeah.
Okay. What you find first, and remember they're always square, okay? And you find the diagonal, the main diagonal, and if it's an upper triangular matrix, everything below the main diagonal is 0, and if you're in a lower triangular matrix, everything above the main diagonal is 0. Now, here's what makes these triangular matrices so wonderful, is the determinant of one of those, you simply multiply your diagonal entry, your main diagonal entries, and that's it. Because everything else is multiplied by 0 from one of those upper or lower triangles. So they I don't see the matrix they were talking about. Perhaps it's the one from, oh, here it is. Okay. Is this the one? No, it's not the one we just did. Yeah, because it wasn't a dark triangle. So I'm going to I've got so many things open at once. Oh yeah. That's not working. Oh, there we go. I couldn't see my little icons down here. Okay. Now, here is a matrix A. 2, 3, negative 1. Negative, or 0, negative 1, 2. 0, 0, 3. Okay? Now, what kind of matrix is that? Are you there?
That's upper.
Upper triangular matrix, absolutely. Can you tell me the determinant of that matrix? Okay.
What's the determinant?
Okay. Here is the old long way to do it. Okay, number one, pick the row or column with the most zeros. That's either the first column or the third row. Let's go with the first column here. That 2 right up there, you know it? You see it? That is a positive position. So it'll be 2 times the determinant of what's left. When you wipe out that row and that column, the determinant that's left is, yeah, 2 times a negative 3 plus 0, right? Well, 2 times negative 3 is negative 6. Okay? Now that was the old way of doing it. Here is the easier way. For any upper or lower triangular matrix, forget about this. Well, don't forget it, but you know. Here's all you have to do. If I can get that erased. Oops, I didn't. Okay? Just multiply your diagonal elements. That's what we just read. 2 times 3 is 6, times minus 1 is minus 6. Don't have to worry about crisscrossing. Don't have to worry about expanding a 3 by 3. Don't have to worry about any of that. Just multiply your main diagonal elements together. That's the determinant. Because these zeros down here wipe out everything else except that one product there. Multiplying by 0 is a wonderful thing if you're trying to make life easy, right? Okay. Now, I don't know for sure if Josh has a book or not, so I'm going to erase it. All right to erase this one?
Yeah.
Okay. Here's theorem 3.2, and this is what we were just doing. If A is a triangular matrix okay, of order n, then its determinant is the product of the main diagonal entries. Pretty ugly writing, but you got it. Okay? Just multiply the main diagonal entries together. Now, of course, if one of those happens to be a 0, that means the determinant of that matrix is 0. And if the determinant is 0, what does that mean? You recall? If the determinant of a matrix is 0, that means it's a
0 vector.
It's a singular or invertible matrix. Okay, I was trying to think of the word. If the determinant of a matrix is 0, that means it's not an invertible matrix. In other words, a singular matrix. So they have a little proof there about the determinant of triangular matrix. We just sort of shown it. So let's do example 6, which is a little more complicated of a matrix, but the answer is just about as simple. Here's matrix A. Well, ooh, that's an ugly A. What makes it more complicated is a 4 by 4. It's a 2, 0, 0, 0. Do you happen to know Josh's number?
Yes. Not off the top of my head, though.
Okay, it's not an 873-7149, is it? Well, it's gone anyway. I hate having my phone in here, but that's my clock. Okay. So anyway, there's the first row of matrix A. 4, -2, 0, 0, -5, 6, 1, 0, and 1, 5, 3, 3. Matrix A. What kind of matrix is that? Besides being an ugly. That's a lower triangular matrix. You're absolutely right. That A is so ugly, I can't stand it. Okay. All right. So what's the determinant of A? That's supposed to be straight lines.
Would 19 be the number?
Okay. Easier than that. Multiply the diagonal elements together. 2 times -2 is -4, times 1 is -4, times 3 is?
Sorry, I've been driving this whole time.
What's that?
I said, sorry, I've been driving this whole time.
Oh, I'm sorry. I didn't know you were in the car.
You're fine.
Hey, if you need to, hey, be careful. Be safe. Don't, get where you're going and come back in. I think you can do that.
I'm parked now, so I'm fine.
Okay. You just multiply the diagonal entries together. Main diagonal, -4 times 3 is -12. You see it? You there?
Yeah.
Okay.
Okay. So where's the main diagonal?
Okay. Do you see the screen?
Yeah.
I drew the line down the main diagonal from upper left to lower right.
Okay.
Multiply those together. -2 times, or 2 times -2 times 1 times 3. -4 times 3 is -12. You see it?
Okay. Yeah, I got it.
All right. Any triangle, upper or lower, that's how you do it. And that finished 3.1. So homework exercises here include any of the odds 1 through 11. They're all at Calc Chat. And by the way, that number 11, whether we get there or not, I don't know if we will, this doing remotely, I don't know if it'll go faster, slower, or whatever. But if you remember in the course description, Chapter 7 is talking about eigenvalues and eigenvectors. You're going to do something that looks a lot like number 11 when you're doing, and 12 too, by the way, when you're doing those, those lambdas there would be your eigenvalues. But we're not there yet, but just that's why that's in here. 13 or 15, they're both at Calc Chat. 17 should be at Calc Chat. Any of the odds 19 to 31 should be at Calc Chat. Those big matrices like 31, find those, well, let's see, not quite a diagonal matrix, but only one number out of being that. Find the column or row with the most zeros in it and start that way. Okay, number 33 should be at Calc Chat. Any of the odds 35 to 38 should be at Calc Chat, and they suggest 35 or 37 should be at Calc Chat. They suggest 37 might need graphing utility to do. I don't think so. It's a simple enough matrix, but anyway, you determine that. 39 or 41, both at Calc Chat, and that 41 I know is a upper triangular, but something else about it, its main diagonal has a 0 entry, so that makes it pretty special too. 43 is a true false, so you can find that hopefully at Calc Chat. 45 or 47 should be at Calc Chat. 47, 49 or 51 should be at Calc Chat. Again, those are going to be precursors to your eigenvalues. 53 should be at Calc Chat. Any of the odds 55 through 61 should be at Calc Chat. 63 through 67 should be at Calc Chat. 69 should be at Calc Chat. All right. Now, any questions? 3.1.
No.
All right. Let's move on to 3.2. By the way, this is my third class of the morning, and you're the first student of the morning, so thank you for being here. All right. Section 3.2, well, I kind of blew it on my first class. I had sent the message to the first class, and I had time. I sent the message to the second class. Then what I didn't realize, I was still in that class in Blackboard when I sent the information for the first class, so no one in the first class got it. The people in the second class, if they were paying attention, said, "What's this guy doing?" And then they missed the second class too. But anyway, at least I got your class right. 3.2 is dealing with determinants and elementary operations, okay? And they have, I'm taking you probably don't have your book there, do you?
No, sir.
Okay, if you're driving, I wouldn't want you to have it open anyway. Here is the determinant of matrix A. 1, -2, 3, 1, 4, -6, 3, 2, -2, 4, -9, -3, 3, -6, 9, 2. That's the determinant of matrix A. Here's the determinant of matrix B. I wish I could get this out of here, but I don't seem to be able to do so. No, it came back. That's a little better, but okay. Here's matrix, the determinant of matrix B. 1, -2, 3, 1, 0, 2, -9, -2, 0, 0, -3, -1, and 0, 0, 0, -1. Now their question, which of those would be easier to calculate the determinant? B for sure, okay? It's an upper triangular matrix. The determinant is the product of that diagonal, right? Here's the reason they're asking such a dumb question. If you did a row reduction of A, you get B, okay? They haven't verified that, but you notice the first row is the same. But if you do -4 times row 1 and add it to row 2, you get a 0, 2, -9, -2. Sure enough, and if you, it takes a little work to get there, but you would produce that. A simple row reduction, okay? Now, what enables us to do that? Oh man, they're actually going to do this thing. Sorry about this. Okay, they're actually going to calculate the determinant of A. Okay, and maybe it's not a bad exercise to do. The really bad news, there's not a single 0 in matrix A, not a 1. So it really doesn't matter which way you go. I'm going to go with the first row, and we'll go across that way. We start with the first entry here. That's in a positive or negative position. That 1 right there. Positive. So that's just going to be 1 times the determinant of what's left over when you wipe these out. And that would be a -6, 3, 2, 4, -9, -3, -6, 9, 2. And since that's a 3 by 3, I'm just going to expand and do -6, 3, 4, -9, -6, 9. Okay? Now that's not really a determinant, even though I'm using that same whatever you call it, symbology, but it's not. So let's do the, okay, that's going to be the first one, okay? Then let's go to the second column in that row. So I'm going to erase this one, and we'll do, wipe out this one, okay? Now, we're going to be using that -2. What's the sign of that position? Negative, so -2 is a +2, and then we'll be doing the determinant of what's left there, and that's going to be a 4, 3, 2, 4, 3, -2, -9, -3, -2, -9, 3, 9, 2, 3, 9. Agreed? Please say yes. Okay. All right? Okay. I'm going to wipe out my construction line for column 2 and go to column 3. Okay. Now what's the sign of that 3 up there in the where the crosshairs are? Positive, so that's going to be a +3 times the determinant of what's left, which is 4, -6, 2, 4, -6, -2, 4, -3, -2, 4. 3, -6, 2, 3, -6. One more to go. I don't know where I'm going to do all the writing that I have to do, but I'll find somewhere. Let's erase that construction line and do the last entry. And what is the sign of that position, that 1 there in the upper right corner?
Positive.
No, that's a negative. See, plus, minus, plus, minus. See what I mean? Upper right corner, not upper left corner. Be a -1 times what's left. 4, -6, 3, 4, -6, -2, 4, -9, -2, 4, 3, -6, 9, oh, 3, -6. I almost wrote my 2 down there. All right. Okay. Let's do our down diagonals. what does that for? Oh, gag. This is messy. The 1, I'm not going to mess with it, just multiply by 1. So what's that first entry? Are you still driving?
Nah.
Oh, okay.
108.
108. Okay. Next entry. 54. Next entry. 'Wait, is that right?
63.
No, okay, you multiply. 2 times 4 is 8 times 9. Right? Or I did 9 times 4 is 36 times 2 is 72. Okay? Now, just to keep from confusing things too much, I'll erase those construction lines and do my up diagonals. That's going to be a what?
-108.
Yeah, negative 108. So I'm just going to wipe out the 108 there. Okay. I'm running out of room fast. This one will be a I have to do that over here. 54 times 3, 162, but it's a negative, isn't it?
-162.
Is that right?
Yes.
Okay. And then this one will be a
-24.
yeah. Okay. Whew. That's just the first one. Now we got to do the second one. Plus 2 times, let's do our down diagonal here. And what's that?
-72.
Okay, let me see. It's 36 times 2 is 72, isn't it? Isn't it? Okay. And this one will be
27.
second,
27.
negative 27. And this one will be a
-36.
right. Okay, I'm going to wipe out my down diagonal line so we can see a little better. Oh, I lost my 2. And make sure it is a 2. Yeah. Okay. Now my up diagonals are going to be a plus 54, is that right?
Yep.
Okay. This one will be a it's 36 by 3, 108.
Yep.
Okay, and this is going to be a plus 12, isn't it?
Yeah.
All right. Here's that one. Now we're going to have a plus 3 times. This is getting old fast, isn't it?
Yeah.
16 times 2 is 32. 9 times 6 is 54. times 6 is 24. I can't believe it. Okay. Up diagonal, minus 24, right? So that's going to wipe out the plus 24. Next up diagonal is going to be a minus 82, is that right? No. 72. I don't know why I can't do that in my head. Is that right? I think so. Okay, and the last one there is going to be a minus 24, isn't it?
Yep.
Okay.
Where is that?
Huh?
No, never mind. I didn't see one of the minus signs.
Yeah. Kind of lost myself. Okay. Then we got a minus 1 times. Whoa. 36 times 4. 144. Plus. So 54 times 3. I did it before, but I didn't write it down. I think it's 162. Yeah. Is that plus? Yeah. Yuck. Computers are wonderful now, aren't they? Okay. That's 6 times 6 is 36, and it's a plus. All right. I think they're just rubbing it in how much easier the other one's going to be. Okay, we have to do the up diagonals. That would be minus 36, right? Wipe out that one. Up diagonal here is another minus 54 times 3. I think that's 162, so that one's gone.
Times 4.
What's that?
And then 54 times 4.
You're right, times 4. Okay. I was so anxious to get rid of one. Okay. 54 times 4 is 216. And that's a minus. And the last one. Goodness, the one I've been waiting for. That's a minus 54 times 2 is 108, isn't it? Okay, now I'm all in favor of grabbing a calculator, which I don't have here in front of me. Oh, well, I do have my phone. Let me see if I can do it here. Okay. 54 plus 72 minus 162 minus 24 plus, I sure hope this does rules of order of operation correctly, plus 2 times a negative 72 minus, no, it didn't do it right. Yuck, I hate that. Okay. I can do it with parentheses. Okay, let me start over. 54 plus, okay. 54 plus 72 minus 162 minus 24 plus 2 times open parentheses, this should work, 72 negate minus 27 minus 36 plus 54 close parentheses plus 3 times open parentheses 32 plus 54 minus 72 minus 24 close parentheses minus 1 times open parentheses 144 plus 162 minus 216 minus 108 close parentheses equal. I get negative, no. I get a wrong answer. But I think the whole purpose of that was just to show you that it's miserable doing it this way. Absolutely miserable. Whereas, if you do B, I can do that one in my head. Positive 6. All right?
Yep.
That was totally unfair of them to do. But you see, there's so many opportunities to make errors in a 4x4 matrix with no zeros in it. Goodness gracious, it's terrible.
So that process is whenever you don't have an upper or lower triangle?
Right.
Okay.
Yeah, any triangular matrix with upper or lower, just multiply the diagonals. That's all. Now, you might think, why did they treat us so badly there? Here's sort of why. What they're going to show you in example 1. So I'm going to erase what I've got here. Okay. And here is the determinant of another matrix A much easier matrix A. The determinant of 2, negative 3, 1, 4. I think I can do that one. What's that? Say again?
5.
Okay. 8 minus a minus 3. So 8 plus 3. 11. Okay. Now here's our matrix B. Now, all I'm going to do to matrix A is swap the 2 rows. 1, 4, 2, negative 3. What's this determinant?
11.
Negative 11, isn't it? Negative 3 minus 8. Negative 11, right? So, at least in this one example, exchanging 2 rows negates your determinant. Okay? Now, the B one. Different matrix A. 1, negative 3. 2, negative 4. What's his determinant? Second? 2. Perfect. Okay. Now this time, our matrix B, we're going to obtain by row reducing. Okay. Minus 2 row 1 plus row 2. You usually don't do that in a determinant, but we're doing it. We could have done it outside in the matrix and came up with it. And so let's see what you get. 1, negative 3 stays the same. What do you get in the second row?
0.
0.
And 2.
2. Now you want to guess what the determinant of B is? 2. It's an upper triangular matrix. Just multiply the diagonal entry and you got it, 2. So, at least in this example, the elementary row operation of adding a multiple of one row to another row doesn't change the value of the determinant. Exchanging 2 rows negates it. Adding a multiple of one row to another row does not change it. Let's see about C. Okay, here's matrix A. 2, negative 8, negative 2, 9. What's this determinant? Whoops.
Yeah, 2.
Is what?
2.
2. Okay. How about this one, B? What we're going to do, another elementary row operation, we're going to divide row 1 by 2 and make that the new row 1. Okay? So what would that be? 1,
Minus 4.
negative 4, negative 2, 9. What's this determinant? 1. So it appears, just with this one little simple example, that by the elementary row operation of dividing or multiplying a row by a non-zero number, you'll divide or multiply the determinant by that same non-zero number. We divided the top row by 2, we divided the determinant by 2. Okay. Or we multiplied the top row by 1/2 and multiply the determinant by 1/2. So this leads us to the theorem, which we see at the top of page 119. And let's see, how are we doing? Yeah, we've got time, I think, don't we? Yeah, we go to 12:45, right? Yeah. Okay, here's theorem 3.3. A and B both have to be square matrices. Now, not only do they have to be square matrices, they have to be square matrices of the same size. Okay. They didn't say that, but it's true. Okay. First, when B is obtained from A by interchanging any 2 rows then of A, then the determinant of B is equal to minus the determinant of A. Okay? That's what we saw in example 1A. It is now in the theorem true. When B is obtained from A by adding a multiple of one row to another, then the determinant of B is the same as the determinant of A, which is a very nice thing to have. Okay? And number 3, when B is obtained from A by multiplying a row of A by a non-zero number then the determinant of B is equal to, and they gave that a name, non-constant, non-zero constant C times the determinant of A. Yeah. Now they have a little proof here, and you can certainly go through and see the proof. Before we get to example 2, there is a little blurb on the left-hand side of your page there, 119, on Augustin Louis Cauchy, I think is how you pronounce his name. His contributions to the study of mathematics were revolutionary, often credited with bringing rigor to modern mathematics. He was the first to rigorously define limits, thank you very much for that, continuity, and the convergence of infinite series. Wow. In addition to being known for his work in complex analysis, he contributed to the theories of determinants, differential equations. Wow. Did a lot. And notice his age there. His picture looks quite young. Well, I don't know if you got your book there or not, but if you do the subtraction there, you see that he lived to be 68, which I guess was fairly old. His picture looked much younger than that, okay? Yeah, 11 and 57 is 68. So he did live to be an older man, but I think a lot of what he did was in his youth. The things I've read or seen about it. But anyway, you can do that. One interesting thing, it's interesting to note that Cauchy's work on determinants preceded Cayley's development of matrices. Now, I have sort of a hard time wrapping my head around that. If you didn't even have matrices there, how in the world did you have determinants? And yet, Cauchy was there and did it. Pretty incredible. All right, let me erase this and move on to example 2. Find the determinant of A, where A is the matrix 0, -7, 14, 1, 2, -2, and 0, 3, -8. Now, frankly, I don't know why they use this as an example here, okay? Because if you chose the first column to work down, you see this 1, that's in which position? A positive or negative position?
Positive.
No, plus, minus, plus. That's a minus. I'll talk about the 1 in the second row, right? So that would be a -1 times the determinant here. 56 minus 42. This would be a -14. Now that's so easy to do that way, but that's not what they wanted you to do. They wanted you to row reduce this and first make this a 1 to -2. I don't know what I would have done next. 0, 7, -7, 14, and 0, 3, -8. Okay, what that did, it made the determinant of A the negative determinant of this thing. You see, because we exchanged a row. Next thing we're going to do is divide row 2 by negative 7. Okay, so that would then be 1, 2, negative 2, 0, 1, negative 2, 0, 3, negative 8. All right, what that would have done was make the determinant of A the positive 1/7 the determinant of this one, right? Okay, I hope I'm going the right direction. I may be going backwards. No, I think I'm going backwards. Oh, we'll see. We'll figure it out in a minute. Okay, then the last step was -3 times row 2 plus row 3 is the new row 3. Okay, and that would then produce 1, 2, negative 2, 0, 1, negative 2, and the last row would have been what? Negative 2, I think, right? Okay.
That makes the determinant -2.
Yeah. Okay. The way they're doing it here actually is a little better. Yeah, that what they did here was basically factor out a -7, okay, which would then be, that was a -1 here, so that makes it a 7 times the determinant of what's left. And then this didn't change at all. This is easy to get the determinant of this one. What is that?
-2.
-2 times a 7 is -14. And what do we get? -14. Now, in many circumstances, it is far better to row reduce. Okay. Now, here's what some of those circumstances are, especially if you don't have to exchange rows or multiply or divide by a constant. Those mess up. If all you're doing is adding a multiple of one row to another, just do it, and your determinant at the end is going to be your determinant of whatever you started with. So yeah, -14 is the answer. All right. How are we doing on time? Oh, we got 5 more minutes. Okay. Now, this starts sort of a new kind of concept here. We have been doing row reductions, but on page 120, they start talking about something very different here. And this only works well with determinants. Don't do this with other things. Although Theorem 3.3 is stated in terms of elementary row operations, the theorem remains valid when the word column replaces row. So operations performed on the columns rather than the rows of a matrix are called elementary column operations, and two matrices are column equivalent, whereas we've been calling them row equivalent. Now, this will mess up your answers when you're getting to trying to solve systems of equation, yeah, you don't exchange columns. You don't do that. But if all you're looking at is the determinant, then you can do whatever you were doing with rows, you can do with columns as well. Okay? For instance, the determinant of 2, 1, negative 3, 4, 0, 1, and 0, 0, 2. Now you could do that relatively easily by using, say, the middle row or the last column, the middle column or the last row. Just by doing that, this would be a minus 1 times 8 would be a minus 8, because that gives you a 0. Okay? That's not too hard to do. But if you were to exchange these two columns, that would give you 1, 0, 0, 2, 4, 0, negative 3, 1, 2. Okay? Exchanging two columns negates the derivative. And what do you get here? That's now a upper triangular matrix. And what do you get? That determinant is 8. When you exchange two rows, it made it a minus 8. So, both of those were awfully easy to do. The second one has the advantages. The math is easier, but you just have to remember you exchange two columns, and that negates the determinant. Okay. That was that example at the top of page 120. How are we doing? I don't think we have time to do the second one. So what we'll do is that will be the first example we do next time. And believe it or not, I haven't ever made a mark on either one of these. Oh, this is a new book, that's why. Okay, so we'll pick up there. Let me give you homework exercises in 3.2. This is sort of a long section, not too long, okay? You can do any of the odds 1 through 19, okay? And they should all be at Calc Chat. I think you could do either 21 or 23. They should be at Calc Chat. And I think you can do any of the odds 25 through 35. They should be at Calc Chat. We'll hold off on the rest of those till we get back. All right. So Thursday, same time, same station. We'll try to meet close to class time every time. I'll try to have a message out there. Now, one thing that didn't happen this time, didn't happen in my first class, it happened in my second, didn't happen on this one. Sometimes, after about 40 minutes, because I'm using the free version, it discontinues. If that had happened, then I would have to go in, open a new class, and start over. I mean, not start over, but start again where we left off. So I would then have to give you another code, and then you would enter that. So it didn't happen this time, but it did happen, like I said, in my second class. Didn't happen in the first or this time. So I can't figure it out. So I guess the usage may determine that. I don't know. All right, that's all I got. Any questions?
No.
All right, well, I'm going to stop the share, so we're going to be cut off, and I guess I'll sort of see you virtually on Thursday. Okay? Well, tomorrow maybe. We'll do the same for Cal 3. All right, see you then. Bye-bye. Okay.